Okay, explore number 3. This is our last explore for the periodic trends. So let's get going. Drawing our Cornell note lines. Today is Tuesday. Okay, go ahead and write whatever date it is that you're writing for these notes. Okay, we're going to give ourselves some space here for the essential question. What other periodic trends besides reactivity occur? Okay. What other periodic trends besides reactivity occur, comma, that's OCCUR, and how are they explained? Okay, question mark. Okay. All right, so we've got quite a bit of work here to do. So let's first go ahead and put down what I know. Okay, take a moment just to write down some thoughts. If you have any additional things that you know about this is a good time to put it down. Also, make sure you've read these notes and watched the videos, or read this page, Explore 3, and watch the videos before you take these notes, okay? Okay, Roman numeral 1. Atomic radius. Okay. Observed periodic trends. Okay, so if you recall, if we take a look at a basic shape like a circle, changes back to 100, you have a circle, and a circle has a radius, which is half a diameter, right? The radius in this picture is going from the center to the edge of the circle. Okay, that's your radius. It's a measure of distance. And you have your diameter, which actually goes from one end all the way across to the other end. Okay, and that we could call your diameter. Okay, so just to kind of refresh ourselves on a little bit of geometry there. So, do the sizes of your atoms, whether you're talking their radius or their diameter, do they follow any particular trends? That's what we're thinking about right now. Okay. So, here in the first paragraph, one measure of atomic size is the distance from the center of the nucleus to the outermost electrons. Okay, so if in an atom, then we're talking about the nucleus, which we'd say is in the center, right? The nucleus might be in the center. And then we may say that you have an electron orbiting, right? There's the electron. So atomic radius in this situation would be from the center of the nucleus. So we could go ahead and say from the center all the way to the edge And that's what they're referring to as the atomic radius. Okay. Atomic radius. Okay. And this would be the outermost electron. Okay. The size of the radius is hard to describe because an electron cloud does not have well-defined surface. That's right, they're moving at the speed of light. We kind of just generally say there's a probability they're going to be here or there. A common way to describe it is half the distance between the nuclei of neighboring atoms. So what they do in this case then is, because it's hard to describe, they use this kind of model. They say, well, what if you have an atom? Okay, and here's your other atom. So if you could just take the distance from the center of the nuclei and divide that by 2, you'd basically have half. So half this distance is equal to your atomic radius. Okay, that's all they're saying there. And they're saying that because it is because these radiuses, these atomic radiuses, it's hard to describe because they are not well-defined surfaces. So this is another way that you can do that. Okay. Now they do say that when it comes down to, and I'm drawing your attention now to paragraph number 2, right here, the atomic radius does not vary much for transition elements. Okay, let's put a little note there to ourselves. Okay. It does not, I should do some black, right? It does not change much. It does not vary much for the transition elements. Okay, and if we look at the periodic table, they're talking about these guys right here, these transition elements, right? Your atomic radius does not vary much for these guys. Okay. Okay, but it does for the main group or the representative elements. So where does this really apply to? It's applying to the 1A, 2A, and to the 3A, 4A, 5A, 6A, 7A, 8A. So to those ones as well. That's what it's applying to. Okay. All right, clear the screen, move on to the next paragraph. For main group elements, the atomic radius increases as you go down a group. Okay, so that's probably really what we want to know here. This is pretty important information. B. The atomic radius increases as you go down a group. Okay, that is good information. Okay, this is good information. All right. This increase results because a new energy level is added as you move from one period down to the other. The outermost electrons occupy different energy levels that are further and further from the nucleus. With each shift to a new period. Okay, so why does it increase? Because, why? Because um, electrons are added to new energy levels, and each energy level is further and further from the nucleus. Okay. Right. So if we jump down to the picture here, you can see the trends that they're trying to show. As you go down, you have an increasing atomic radius. Now, another thing that's worth noting is also when you go from right to left. You also have an increasing atomic radius. Okay? What could be causing that? Okay, we just explained the idea of additional energy levels causing your atomic radius to increase, but what would explain the atomic radius getting bigger as you go from right to left? Okay. You got a few videos here. Here we have kind of a duplication of information. Okay. Okay. Atomic size, the effect of nuclear charge. Let's see if they're going to reveal this answer to us, okay? The decrease in atomic size across a period can be explained by the effect of increasing nuclear charge. As you move from left to right within a period, the numbers of protons and electrons increase. This increases the amount of positive charge. Since the electrons are being added to one energy level, they occupy the same region. As a result, they are held more tightly by the increasing positive charge of the nucleus. Okay, so I think they just told us the answer there. Let's try to get back up to a picture here. Okay, as you are on the right-hand side of your chart here, if you take a look at something like, let's see here. Let's see, they got magnesium as 160, and they have chlorine as 99. Let's just kind of double check some things here, okay? Okay, I think those numbers are something a little bit different there. But let's use this periodic table just to kind of give us a reference, okay? If you're talking about something like sodium, okay, so first let's write this down, okay? Also, atomic radius increases from right to left. Okay. And the explanation they gave was consider sodium, for example. Sodium has 11 positive charges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And it has 3 energy shells. 1, 2, and 3. And if you were to go over to something like, say, go to sulfur, which is in group 16, let's just say sulfur versus sulfur. Sulfur has 16 positive charges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And it has still 3 shells. 1, 2, and 3. So what's happening is you've added more electrons, but those electrons are still only going to be on that 3rd shell. Okay. So sodium we said had 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the sulfur had 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these electrons, even though you add more electrons, they're still on the same energy level, but you have a whole lot more positive, okay? A much stronger positive pool, right? So what happens is these guys are going to be pulled in a lot tighter. Everything's going to get pulled in a lot tighter. And this is going to make your atom actually shrink. It's going to become smaller because you have a really strong positive pull on the inside. And that's why as you are on the right-hand side of the periodic table, things are small, right? Smaller. And as you go this direction, things get larger. Okay, so that was kind of the example. Hope that helps. Okay. All right, let's keep on going here. Let's jump down to atomic size. As you move left to right, this increase in non-positive charge. Okay, we just talked about that. All right, so let's go down to the next part here. Factors underlying periodic trends. Okay, what do we want to say here? Atomic radius. We'll go and call this number 2, okay? Roman numeral 2. Factors underlying periodic trends. Okay. The factors that explain the observed trends in chemical reactivity and atomic radius apply to other properties of the elements. So not only is there chemical reactivity, which we talked about in the previous Explorer, not only is there atomic radius, which we just talked about, other important factors are what? The total number of electrons in an atom, the size of the nuclear charge, the distance between the nucleus and the outermost valence electron, and the amount of shielding. Okay? And they show a nice little graphic. All other periodic trends can be explained using these 4 factors. Okay? So factors underline periodic trends. Okay. Periodic trends can be explained by what? They can be explained by the following things here. They can be explained by the size of nuclear charge. Remember that sulfur versus sodium example had more protons. Periodic trends can be explained by the distance. The distance from nucleus to valence electrons. Periodic trends can be explained by shielding of electrons. From nuclear charge. And periodic trends can be explained by the number of electrons. Okay, so we have these four factors. Okay, there's four of them. Four factors underlying your periodic trends. Okay, keep that in mind, okay? Got a nice little exploration simulation to practice with. Periodic trends in ionic radius. Okay, we just talked about atomic radius. What's this business about ionic radius? Well, if you think about what an ion was, it's an atom that either gains or loses an electron, and you become a positive or negative ion, right? So periodic trends in ionic radius. Okay. An ion is a charged particle that results when an atom loses or gains electrons. The charge results from an imbalance in the number of protons and electrons. Okay, we got that. We understand that. This is just some old information, you know. Ionic radius is the distance from the center of the nucleus to the outermost electron of an ion. Okay, that's really the only difference. Okay, it's very similar to an atomic radius. Okay, so ionic radius it is the distance from the center of the nucleus to the outermost electrons of an ion. Instead of atom, we're using the word ion. Okay, that's the key. All right. What do we say? They're hard to describe, just like atomic radius, because electrons are all over the place. Metal atoms become ions by losing electrons. These ions are smaller than their neutral atoms because there is more pull by the nucleus on the electron in the outer energy level. So we're reading this part right here. Okay, we just read that. Okay, so let's put down a capital A. Metal atoms become ions by losing electrons. Right, so if we were to use any of these examples, like let's just say in our group 1, for example, you have lithium and sodium and potassium and rubidium and cesium and francium. They all have one electron in their valence. it is more favorable energetically to just lose that electron. In so doing, they'll drop down in energy level and gain a full valence by doing that. Okay, but in that process of losing their electron, they become a positively charged ion. That's what we're saying here. Okay, metal atoms become ions by losing electrons. These ions are smaller than their neutral atoms because there's more pull by the nucleus on the electrons in the outer energy level. Okay, let's put a little star here because we're talking about size, right? The ions are smaller than their neutral atoms. Why? Because you have more positive pull on by the nucleus. Because more positive pull from the nucleus. Okay, because they lost one electron. Okay, so there's like this imbalance. Non-metal atoms, so now we're talking about things on the right-hand side of the periodic table, become ions by gaining electrons. Remember your non-metals, right? So we're talking about things like these guys. They tend to gain an electron. Carbon has 14, 15, 16, it needs 4 more electrons. Oxygen has 16, right? Oxygen has 16. Or 6. It just needs 2 more valence electrons, right? So non-metal, we'll call this letter B, become ions by gaining electrons. And in so doing, they're going to have an imbalance. They're going to become more negative. And let's put that down. So they become more negative. More negative, right? What we call an anion. Okay, and what did we call the metal atoms that lost electrons? They became more positive. We call them cations, become more positive, called cations. These are words you're going to be hearing in the future, so you might as well kind of try them on for size, okay? Now, about size, speaking of, these ions, non-metal, are larger than their neutral atoms because the pull of the nucleus on the electrons is weaker. Okay. The ions of what? Of non-metals, right? We're talking non-metals, are larger than their neutral atoms. And why is that? Because the pull of the nucleus on the electron is weaker. Because the nucleus exerts a weaker pull. Okay, and this is by nature of it having more electrons. Okay, a weaker pull. Okay, that's I think that kind of explains it. And so you have some pictures over here. You can see where you have your neutral. This is your neutral atom, and these are your ions. Okay, these are in group 2A. Again, you have your neutral. You have your neutral versus your ions. Okay, and they kind of go through this here. Ionic radii differ from atomic radii, but follow the same general trends within a group and across a period, as shown by the chart for metals. Okay. All right, let's talk about other things here, okay? Periodic trends in metallic character. Okay, what's that all about? I think this is going to become number 4 for us, okay? Okay. We're going to say Roman numeral 4. Right, Roman numeral 4. Periodic trends in metallic character. Okay. And what are they talking about? Metallic character is the measure of how easily an atom loses or gains electrons. So let's just put over here, metallic character. What are we referring to? How easily atoms gain or lose electrons. Okay, that's what we're talking about there. Okay. If you jump down here to paragraph 3 in this section here, it says the addition of new energy levels as you move down a group has 2 effects. The distance between the nucleus and the outermost electrons increases, and greater numbers of energy levels occupy this distance. The shielding effect of the inner electrons and the increasing distance reduce the effective nuclear charge experienced by the outermost electrons. As a result, less energy is needed to remove one outer electron, and so metallic character increases. So as you go down, so A, going down the periodic table, this is kind of having a hard time. Going down the periodic table, we see increase in energy levels. Therefore, more shielding. Okay, so that's like saying you have a nucleus and you have, here's your nucleus, and you have, let's just say you got one energy level versus if you go down the periodic table, maybe you have another one where you have a nucleus, but this nucleus has 1, 2, 3 energy levels. And so you have more electrons blocking. Right? So this is that shielding effect. Okay, and what does that make? It makes it easier to lose. It's easier to lose. Therefore, it's more metallic. Because being more metallic by nature is to be able to lose electrons easily. Okay. Now, within a period, if you go across, only the nuclear charge factor is at work. Okay, there's not additional energy levels. The number of protons increases as you move from left to right, but no new energy levels are introduced. Therefore, as you move from left to right, the outermost electrons experience a greater and greater positive charge from the nucleus, and it becomes more difficult for an electron to be removed. Metallic character decreases as a result. Okay, so let's put that down for letter B, okay? Okay, we're going to say letter B. Going across a period, metallic character decreases. Decreases. And the reason why is if you have a nucleus, i.e., nucleus with two charges, and then you go all the way over to one that's got a nucleus, and that one has, let's just go ahead and say we have 1, 2 there. And here we're going to say that you have 1, 2, 3, 4, 5, 6. If they both have the same number of energy levels, the only difference is the number of protons, then these protons are going to pull harder. They're going to attract electrons more. Attract electrons more. Therefore, these become less metallic because they do not want to lose their electrons, okay? And so that's kind of what it's saying there, okay? And this is just stuff you're going to have to review, quite honestly, over and over. But you can see the overall trends. Metallic character increases going from top to bottom, and metallic character decreases going left to right, okay? Rules, okay? So let's just say letter C, refer to chart. But that basic idea was that with your periodic table, if this is your periodic table, if this is your P table, what do we say about metallic character? Metallic character increases this way, and metallic character increases going this way. Okay, that's what we're trying to say there, okay? All right. Let's keep on going here. Ionization energy. We're going to call this what? What do we want to call this here? this will be number 5, okay? Number 5. Roman numeral 5. And we're talking about periodic trends. And ionization energy. Okay. What is ionization energy? The energy needed to remove one electron from the outermost energy level of a gaseous neutral atom to form an ion having a positive 1 charge. There you go. You always wanted to know. Now you know. Okay. The energy needed to remove 1 electron from the outermost energy level of a gaseous neutral atom to form an ion of a gaseous neutral atom to form an ion having a +1 charge. Okay, so the energy required to remove the outermost electron from the gaseous +1 ion is called the second ionization energy. It is larger than the first ionization energy, and the third ionization energy is higher than the second. This is because fewer electrons remain to shield the nucleus from the electrons, and its pull is stronger on the remaining electrons. Thus, each successive electron removed from the atom feels an increasingly stronger effective nuclear charge. As shown in the ionization energy chart, ionization energy decreases as you go down within a group and increases as you go from left to right. All right, well, so let's maybe draw ourselves an atom. Okay, so we've got our nucleus. Okay, we have our nucleus. And we have, let's say, a couple orbits. Okay. And we have some electrons. Okay. And let's just say that here's our electron here. The energy required to remove the outermost electron from the gaseous +1 ion is called the second ionization energy. All right, so if we take away one of these, okay, if we were able to remove one of these, okay, that's your ionization energy. Okay, this is your ionization energy. Now, what happens if you are going to remove another electron? Okay, well, if you were to take away the second one, if this is your first electron, what happens when you take away the second one? Okay, that's what they're referring to as your second ionization energy. Is that going to be easier or more difficult? Well, it is a larger energy. Okay, what happens if you take a third one? If you take a third one, well, that's going to even be a higher, um, uh, even larger ionization energy. And the reason why is because every time you remove an electron, you have more and more positive charge holding on to the remaining electrons. And that positive charge starts to pull stronger and stronger. Okay, so this pull becomes stronger and stronger. The positive pull of the nucleus increases, okay, with each successive electron that's pulled away. Okay. All right. I know there's a lot to say here. And so you can see here, ionization energy decreases going down and it increases going right. All right. So let's just try to draw some lines there. If we were to draw our periodic table, we could say that the trend is to increase that way, or actually decrease. So ionization decreases. And as we go this way, what can we say? Ionization increases. Okay. All right. So these are your trends. And we're just trying to get you guys familiar with that, right? All right. Okay. In addition, the addition of new energy levels as you move down a group has two effects. The shielding thing again. The shielding of the inner electrons and the increasing distance reduce the effective nuclear charge experienced by the outermost electrons. Less energy is required to remove an outer electron. This increases the metallic character, but it decreases the ionization energy. Okay. I would say to pay attention to that. Okay. Within a period, only the nuclear charge factor affects metallic character. So going across, the number of protons increases as you move from left to right, but no new energy levels are introduced. Therefore, as you move from left to right, the outermost electrons experience a greater positive charge from the nucleus. More energy is required to overcome this pull. Therefore, the metallic character decreases, but ionization increases, okay? So this is talking about within a period, okay? And up here, they're talking about within a group, okay? Okay, as you move down a group. That's what they're talking about there. And that's what we have on our pictures here as well, okay? But if you want to get down to it, what could we say? Ionization energy decreases. Why? It's the shielding effect because of shielding. And why does ionization increase over here? Because of increased nuclear charge. Okay, more positive charge as you move from left to right. Okay. All right. Clearing our screen and moving on. And we're almost finished, guys. Hard to believe, I know. Let's do this here. Erase this part here. And I believe this is going to be what, number 7, perhaps? Or number 6? Periodic trends in electronegativity. Yeah, we're going to be on number 6 now, okay? Number 6. Periodic trends in electronegativity. Okay. All right. What is electronegativity? It is the tendency of an atom to attract electrons. The tendency of an atom to attract electrons. Okay. And electronegativity decreases as you go down within the group and increases from left to right. Okay. Well, let's go and just draw that out, okay? And this is just a periodic table. And our general trend decreases as you go down, and as we go this way, electronegativity increases. Okay, and remember, this is the tendency of an atom to attract electrons. So you're right to think then that this is going to have something to do with shielding. It's going to have something to do with nuclear charge, right? I hope you're starting to see this kind of trend that's starting to develop here. Okay. And this is going to be our last little bit of notes for these two paragraphs. As you move down the group, the distance between the nucleus and the outermost electrons increase. Also, more energy levels filled with electrons shield the outermost electrons. So you have both what's going on here because of increased distance. Right, we're talking from the nucleus to the electrons, and because you have shielding. Okay. And both factors decrease the effective nuclear charge. This decreases the positive pull of the nucleus on the electrons, which decreases the element's electronegativity, right? The atom has more difficulty holding on to the electrons, okay? Talking about going from top to bottom. Moving from left to right within a period, however, the atom gains protons and electrons, but no new energy levels form. Therefore, as you move from left to right, the outermost electrons are added to the same energy level. The added protons in the nucleus cause a greater positive charge, which pulls on the electrons. This increased positive pull makes elements more electronegative. Okay, so electronegativity increases because you have increasing positive nuclear charge, and that's holding on to the electrons. All right. I want you to think about all these things in the context of reactivity. Okay, there's a lot that you guys had to digest just now. So let's take a moment. I know you're tired, but let's go and try to write ourselves a summary sentence, okay? All right, and that's it. Good job, guys. We'll talk to you soon.